Hello friends, welcome back to my YouTube channel Journey with Vijay Kumar Shrivastav. Today I am going to present the topic soil pH and soil organic carbon. Before presentation I would like to introduce myself. I am Vijay Kumar Shrivastav. I have done M.Sc Agriculture with specialization in Agronomy from Pant University of Agriculture and Technology in 1996. Hope this presentation will be very useful to all of you. So let's proceed to the presentation. What is soil pH? Soil pH is a measure of acidity or basicity, means alkalinity of a soil. pH is defined as the negative logarithm base 10 of the activity of hydronium ions, H plus ions, or more precisely H3O, in a solution. In soils, it is measured in a slurry of soil mixed with water or a salt solution such as 0.01 m CaCl2 and normally falls between 3 and 10, with 7 being neutral. Acid soils have a pH below 7 and alkaline soils have a pH above 7. Ultra-acidic soils having pH less than 3.5 and very strongly alkaline soils have pH more than 9. Soil pH is the negative logarithm of hydrogen ion activity. The pH of a soil is one of the most important properties involved in plant growth. There are many soil pH relationships including those of ion exchange capacity and nutrient availability. For example, iron compounds decrease in solubility with increasing pH, resulting in many instances where a high soil pH, means under soil alkalinity, causes iron deficiency for plant growth. Soil pH is considered a master variable in soils as it affects many chemical processes. It specifically affects plant nutrient availability by controlling the chemical forms of different nutrients and influencing the chemical reactions they undergo. The optimum pH range for most plants is between 5.5 to 7.5. However, many plants have adapted to thrive at pH value outside this range. Soil pH is determined by the concentration of hydrogen ions H+. It is a measure of the soil solution's acidity and alkalinity on a scale from 0 to 14. Acidic solutions have a pH less than 7, while basic or alkaline solutions have a pH greater than 7. By definition, pH is measured on a negative logarithm scale of the hydrogen ion concentration. Therefore, as hydrogen ion concentration goes up, pH value goes down. Also, because pH is a logarithm function, each unit of the pH scale is 10 times more acidic than the unit above. For example, a pH 6 solution has a 10 times greater concentration of hydrogen ions than a pH 7 solution and a 100 times higher concentration than a pH 8 solution. Soil pH is influenced by both acid and base forming cations, positively charged dissolved ions in the soil. Common acid forming cations are hydrogen, aluminum and iron, whereas common base forming cations includes calcium, magnesium, potassium and sodium. Soil pH is a measure of the concentration of hydrogen ions in the soil solution. Low pH value less than 5.5 indicate acidic soils, high pH value more than 8 indicate alkaline soils, and soil pH between 5.5 and 8 is not usually a constraint to crop or pasture production. A pH of 6.5 is just about right for most crops and home gardens, since most plants thrive in the pH range 6 to 7, which is slightly acidic to neutral range. Some plants like blueberries and azaleas prefer more acidic soils, while a few like ferns and asparagus do best in soils that is neutral to slightly alkaline. Soil pH is important because it influences several soil factors affecting plant growth such as nutrient leaching, nutrient availability, toxic elements, soil structure and soil microorganisms like bacteria. Inherent factors that affect soil pH includes climate, mineral content and soil texture. Natural soil pH reflects the combined effect of the soil forming factors like parent material, time, relief or topography, climate and organisms. The pH of newly formed soil is determined by the minerals in the parent material. Now we will study about soil pH management. Soil pH is affected by land use and management. Vegetation type impacts soil pH. For example, areas of forest land tend to be more acidic than areas of grassland. Conversion of land from forest land or grassland to cropland can result in drastic pH changes after a few years. These changes are caused by a loss of organic matter, removal of soil minerals when crops are harvested, erosion of the surface layer, and effects of nitrogen and sulfur fertilizers. Addition of nitrogen and sulfur fertilizers can lower soil pH over time. Now we will study about changes in soil pH. Soil tends to become acidic as a result of first one, rainwater leaching away basic ions like calcium, magnesium, potassium and sodium. Second, carbon dioxide from decomposing organic matter and root respiration dissolving in soil water to form a weak organic acid. And third, formation of strong organic and inorganic acids such as nitric acid and sulfuric acid from decaying organic matter and oxidation of ammonium and sulfur fertilizers. Strongly acid soils are usually the result of the action of these strong organic and inorganic acids. Now to study about measures to limit or correction of acidification. First one, liming to raise the pH of an acidic soils. Applying nitrogen and sulfur according to crop needs. Apply nitrogen fertilizers in appropriate amount in a timely manner relative to crop uptake, and use of good irrigation management to minimize nitrogen leaching. Then diversified crop rotations to interrupt acidifying effects from nitrogen fertilizer application. Then applying irrigation water, manures and other organic materials that have a high content of calcium or magnesium bicarbonates, and use of continuous no-tillage over crops, applications of solid manures and diverse rotations and high residue crops in order to increase organic matter content and improve soil buffering capacity to limit changes in pH. For correction of acid soils, lime is usually added to acid soils to increase soil pH. The addition of lime not only replaces hydrogen ions and raises soil pH, thereby eliminating most major problems associated with acid soils, but it also provides two nutrients, calcium and magnesium, to the soil. Lime also makes phosphorus that is added to the soil more available for plant growth and increases the availability of nitrogen by hastening and decomposition of organic matter. Liming materials are relatively inexpensive, comparatively mild to handle, and leave no objectionable residue in the soil. Some common liming materials are: first one, calcic limestone, which is ground limestone. Second is dolomite limestone from ground limestone, high in magnesium. And third, miscellaneous sources such as wood ashes. The amount of lime to apply to correct a soil acidity problem is affected by a number of factors, including soil pH, soil texture like amount of sand, silt and clay, then soil structure and amount of organic matter. In addition to soil variables, the crops or plants to be grown influence the amount of lime needed. In addition to monitoring soil pH, the nutrient status of the soil should be examined. Now here to study the pH effects on nutrients, minerals and crop growth. The effect of soil pH is great on the solubility of minerals or nutrients. 14 of the 17 essential plant nutrients are obtained from soil. Before a nutrient can be used by plants, it must be dissolved in soil solution. Most minerals and nutrients are more soluble or available in acid soils than in neutral or slightly alkaline soils. Phosphorus is never readily soluble in the soil, but it most available in soils with a pH range centered around 6.5. Extremely and strongly acid soils having pH 4 to 5 can have high concentration of soluble aluminum, iron and manganese, which may be toxic to the growth of some plants. A pH range of approximately 6 to 7 promotes the most readily availability to plant nutrients. Then soil pH can also influence soil plant growth by its effect on activity of beneficial microorganism bacteria that decompose soil organic matter are hindered in strong acid soils. This prevents organic matter from breaking down resulting in accumulation of organic matter and the tie-up of nutrients, particularly nitrogen, that are held in the organic matter. Now we will study about inherent factors which are affecting soil pH. Inherent factors affecting soil pH such as climate, mineral content and soil textures cannot be changed. Natural soil pH reflects the combined effects of soil forming factors like parent material, time, relief or topography, climate and organism. The pH of newly formed soils is determined by minerals in the soil parent material. Temperature and rainfall controls leaching intensity and soil mineral weathering. In warm, humid environments, soil pH decreases over time in a process called soil acidification due to leaching from high amounts of rainfall. In dry climates, however, soil weathering and leaching are less intense and pH can be neutral or alkaline. Soils with high clay and organic matter content are more able to resist a drop or rise in pH, have a greater buffering capacity than sandy soils. Although clay content cannot be modified, organic matter content can be changed by management. Sandy soils commonly have low organic matter content, resulting in a low buffering capacity, high rates of water percolation and infiltration, making them more vulnerable to acidification. Now we will study about soil organic material. Soil organic matter is the combination of plant and animal residues at various stages of decomposition and cells and tissues of soil organisms. The consistent benefit of soil organic matter is that it buffers soil pH change. Soil organic matter offers many negatively charged sites to bind hydrogen ion in an acidic soils or from which to release hydrogen ion in a basic soil, in both cases pushing soil solution towards neutral. Whether soil organic matter changes soil pH in the long term depends on many various factors. Here we have shown the picture which reflects the biogeochemical processes and their relations with soil pH. Soil pH is a great relationship with mineralization of organic matter, ammonia volatilization, precipitation of organic matters and heavy metals, then soil enzymes activity and biodegradation of organic pollutants, microbial ecological indicators and dissolution of organic matter and heavy metals, rhizosphere processes, organic amendments and nitrification and denitrifications. So all these biological processes or biogeochemical processes are linked with soil pH. Any changes in soil pH will reflect the impact on all these activities. Here we have shown the picture showing the relation between soil pH and organic matter. In case of soils having high soil pH, there will be processes like microbial decomposition of carbohydrates, mineralization to ammonium, volatilization loss of ammonia gas, and high plant residue base forming cation contents. There will be large amount of residues and soil pH will be less than soil organic matter pH. While in case where the soils are having the pH low, then the process will follow like nitrification to nitrate, then leaching loss of nitrate, low plant residue base forming cation content, a small amount of residue will be there and soil pH will be less than soil organic matter pH. Now we will study about soil organic carbon. Soil organic carbon is the component of soil organic matter. The term soil organic matter is used to describe the organic constituents in soil in various stages of decomposition, such as tissues from dead plants and animals, materials less than 2 mm in size, and soil organisms. Soil organic matter turnover plays a crucial role in soil ecosystem functioning and global warming. Soil organic matter is critical for the stabilization of soil structure, retention and release of plant nutrients, and maintenance of water holding capacity, thus making it a key indicator not only for agriculture productivity but also environmental resilience. The decomposition of soil organic matter further releases mineral nutrients, thereby making them available for plant growth, while better plant growth and higher productivity contribute to ensuring food security. Soil organic matter can be divided into different pools based on the time needed for full decomposition and the derived residence time of the products in the soil depending on the turnover time, which is as follows. Like in active pools, the turnover is in months or few years, while in case of passive pools, turnover will be up to thousands of years. Soil organic matter contains roughly 55 to 60% carbon by mass. In many soils, this carbon comprises most or all of the carbon stock referred to as soil organic carbon, except where inorganic forms of soil carbon occur. Similar to soil organic matter, soil organic carbon is divided into different pools as a function of its physical and chemical stability. First one is fast pool, also known as labile or active pool. After addition of fresh organic carbon to the soil, decomposition results in a large proportion of the initial biomass being lost in 1 to 2 years. Second is intermediate pool, which comprises microbially processed organic carbon that is partially stabilized on mineral surfaces and or protected within aggregates with turnover times in the range of 10 to 100 years. Third is slow pool, also known as refractory or stable pool. This is highly stabilized soil organic carbon, enters a period of very slow turnover of 100 to more than 1000 years. The separation of soil organic carbon into different pools is largely more conceptual than measurable and is based on the use of soil organic carbon oxidation or degree of physical stabilization within aggregates or through attachment to minerals determined through analytical protocols. Although soil organic carbon pools are often used to model carbon dynamics, ways to reconcile measurable and modelable pools have rarely been reported. Soil organic carbon and soil organic matter should therefore also be considered as a continuum of organic material in all stages of transformation and decomposition or stabilization. The proportion of labile soil organic carbon to total soil organic carbon rather than the total soil organic carbon pool influences soil organic carbon sequestration and soil health. The labile carbon fraction has been shown to be an indicator of key soil chemical and physical properties. The resistant or stable fraction of soil organic carbon contributes mainly to the soil nutrients holding capacity, cation exchange capacity. Additionally, because this fraction of organic carbon decomposes very slowly, it is especially interesting in terms of long-term soil organic carbon sequestration. When dealing with carbon dioxide, soil organic carbon sequestration involves three stages. First one is removal of carbon dioxide from the atmosphere via plant photosynthesis, and second, the transfer of organic carbon from carbon dioxide to plant biomass, and third, the transfer of carbon from plant biomass to the soil where it is stored in the form of soil organic carbon in the most labile pool. This pool is characterized by the highest turnover rates, which is taking terms from days to few years, encompasses recently incorporated plant residue and is readily decomposable by soil fauna, generally causing carbon dioxide emissions back into the atmosphere. Therefore, imperative soil organic carbon sequestration action planning requires looking beyond capturing atmospheric carbon dioxide and necessitates finding ways to retain carbon in the slow organic carbon pool. Constructingly, research shows that the stable pool has a negligible potential for carbon sequestration due to its resistance to change and hence irresponsiveness to the management. Soil organic carbon is one part in the much larger global carbon cycle that involves the cycling of carbon through the soil, vegetation, ocean and the atmosphere. While carbon dioxide and methane are the main carbon-based atmospheric gases, autotrophic organisms, mainly plants, as well as photo and chemoautotrophic microbes synthesize atmospheric carbon dioxide into organic material. Dead organic material, mainly in the form of plant residue and exudates, is incorporated into the soil by soil fauna, leading to carbon inputs into the soil through organic material transformation by heterotrophic microorganisms. This organic material transformation process results in a complex biogeochemical mixture of plant, litter compounds and microbial decomposition products in various stages of decomposition that can be associated with soil minerals and occluded within aggregates, enabling soil organic carbon persistence in soil for decades, centuries or even millennia. In principle, the amount of soil organic carbon stored in a given soil is dependent on the equilibrium between the amount of carbon entering the soil and the amount of carbon leaving the soil as carbon-based respiration gases resulting from microbial mineralization and to a lesser extent leaching from the soil as decomposed organic carbon. Locally, carbon can also be lost or gained through soil erosion or deposition, leading to the redistribution of soil at local, landscape and regional scales. Levels of soil organic carbon storage are therefore mainly controlled by managing the amount and type of organic residue that enter the soil and minimizing the soil carbon losses. So this presentation was all about soil pH and soil organic carbon. Hope this presentation will be very useful to all of you. Thanks for your kind attention. I have given here my YouTube channel details, Journey with Vijay Kumar Shrivastav. Having request, please visit the channel, subscribe it and provide your kind and valuable feedback for further improvements in next coming presentations. Thank you.